All right, here we go again. How are you doing? Assuming people are trickling in. Awesome, awesome. I don't know if I should do an intro. I don't know if it's worth me doing an intro or if I should just get into it. Let's get rid of this. Cool. So, I've been poking around. I've been thinking about what we did yesterday, and I guess right off the bat, it would be good to correct a few things, right? So we had this make file and we had some problems with it. So we've got these problematic lines here, right? These lines were giving us strife. I'm gonna hit the ground running today, okay? These lines were giving us strife because we're trying to include things for when we run Docker build, right? So when we're in this Docker step, in this like Docker image, we want to include these things. When we're not in this Docker image, we don't want to include these things. That's a problem, okay? I think there might be a way to include things inside a step. I don't think it's as simple as just copying this to be inside that step. What I actually want to probably do is just say like if def. I'm pretty sure there's an environment variable platform that I defined in this Docker file. It might actually be worth copying the Docker file in here as well. Docker file dot. Let's suss what's in this Docker file. Oh, sorry, there's one more thing I want to do. I'm going to put this all on Git at some point, and I'm going to make a new branch right now. 0801. Okay, awesome. So if you're watching these streams, you can come back, you can follow through the Git history. There'll be a branch for each stream and for the work that gets done in that stream. And, you know, I'll probably have like other more meaningful branches and maybe tags and stuff as we go. At some point, I'm going to add some like quality checks to this as well, like a linter and maybe a code formatter. We're going to do some cool stuff. But anyway, for now, makefile, we've got this thing. I'm fairly sure now if I do make Docker build, it'll complain that Docker maybe isn't. Yeah, I need sudo. Perfect, and that now runs. We did it. We solved it. That was a dumb thing to run into right away. Cool. The other thing that I want to fix, when I make, for some reason, it's not actually building the ISO target by default. Which is weird. And it's probably because of this Docker build step, right? This makefile doesn't know how to build EEBin. This makefile knows how to build EEBin. So if we just call make all, it's not going to work. So actually, what we probably want, do I make ISO target? Maybe like build the whole thing? Yeah, sweet. So that's going to work a little bit better now. That's going to be cool. So that's a nice simple thing to start off with, a nice easy win. Let's load up PCSX2 and have a look at what we were doing as well. ISO selector, this is the correct ISO. Sure, okay, it's going to make us check again. So we're pushing a buffer out to the graphics synthesizer, which is basically just a glorified rasterizer. Sorry, I'm sitting on something. I'm sitting on one of my masks. Problems I never thought I would have before the year 2020. Okay, so I am unmuted and everything, aren't I? Yeah. Good. So I realized there's a mistake in this code. We're setting up the graphics synthesizer. You know, we have our initialization code, main.c. So in GS init, we set up a frame buffer, we set up the screen. I actually don't know if we technically need to set up a frame buffer as much as we could just like pick an arbitrary spot in memory. But anyway, that's essentially what we're doing, right? And we're telling the graphics synthesizer where we want to draw to. We're setting up this offset X and offset Y, and this might be a source of drama. I've been having a bit of a look at how PS2SDK handles this. I've been referring to the system hardware manuals. And I'm a little bit confused about this. So offset X, offset Y could be problematic for us. But for now, I think we're okay. The thing we're not doing here, there's a special register in the graphics synthesizer. So let me draw a picture of this, okay? So we have our graphics synthesizer, right? This is our G S. And this is what takes in a list of vertices and outputs to the screen, or to our frame buffer essentially, the data for lines and triangles and points and all those lovely primitives you might want to draw. And then it also knows how to present that to the actual display, right? There's like a analog signal generator attached to this, whatever. The graphic synthesizer has registers. And these aren't registers like you might see if you're programming in like x86. These are registers for things like X, Y, Z. I think we're using XYZ2 or maybe XYZ3. I think it's XYZ2 we're using. There's a register for R, G, B, A, Q, a very interesting format. There's a register for ST, which are like texture coordinates. There's a register for prim, which is the type of primitive you're drawing. Okay, so these registers. So the vertex position, vertex color, texture coordinates for the vertex. What kind of primitive are we drawing? And this is something that doesn't change vertex to vertex. I believe we would be able to set this once. We could just set this to triangle once, and then every vertex, every list of vertices we push through the pipeline will get treated as if it's a triangle. I don't think we have to set this like every frame even. I think this can literally be set once in our program. But right now, we're sending XYZ2, we're sending RGBA color information. We are not telling it what kind of primitive we're drawing. So we need to do that. And that means that we need to go into our GIF tag. We're going to have to modify the information we're sending. So just as a quick refresher, this double word here, this 64-bit number, these every 4 bits, every single hexadecimal digit here is going to represent one register. So in this case, 1 is the color register, the RGBAQ register, and 5 is the XYZ register. So we're sending color data, position data, color data, position data, color data, position data. So what we want to do is shift this over by 1, and we want to put, I don't know what the value is, so I need to look that up, and I'm going to look that up off screen in the hardware manual. I'm not showing the hardware manuals on screen because they are copyrighted by Sony. I probably shouldn't even have it, but nonetheless I do. So register. The prim register is actually register 0. Beautiful. And so now we need to come in here. Again, a quick refresher on this format. This is the number. So we send 7. We're sending 7 registers. We're filling 7 registers in each, I guess, packet of this communication, or in each like loop of this communication. So this 6 is now a 7. We had 6 registers before. We've now added an extra one, and we're still only having one loop. We're still only drawing one triangle. And this bit still needs to be set because this is still the last packet we're sending. So now, before our loop, where we're looping over here, we just need to set the primitive register, and that is done. Where are we? Prim. That's just that's 10 bits of a 128-bit word. That's pretty wild. So Q, DW, 0, the lower bit. No, the lower bit. So and this is something else that's kind of hard to follow. The bottom bit of these numbers is in the first index, I think, right? I think that's how this works, because that's how this one worked. The primitive, does this tell us what the primitive, this doesn't tell us what the primitives actually are. I think these are defined somewhere in PS2SDK. If we just do a quick search, prim, yeah, here we go, GS prim triangle, that's the one we want, equals, we should just be able to GS prim triangle. And then Q++. Maybe we should 0 out the other double word as well, just to be safe. I don't need to. There we go. Cool. So we've added an extra bit to our GIF tag, and let's see what happens. Cool. Okay, we've got a syntax error. I forgot something. I learnt yesterday typos while streaming are very easy to come by. Did I have? Hold on. Was I? Yeah, we're good. Okay. GS prim triangle is undeclared because that is defined in this awesome header GSGP. So let's quickly just add that. GP. GS prim I think GSPrim triangle, gsgp.h. First use. Oh, it's another typo. It's another bloody typo. Okay, so triangle. Beautiful. Let's see what happens when we run this. I'm hoping to see something on the screen, but I'm not optimistic. I mean, it runs. We're sending this extra primitive information now, which is good. We're making progress. We're making progress. Okay, we've picked up something which we forgot last time. I just need to quickly check my phone here. All right. So, we're setting everything up correctly. I'm pretty confident we're setting everything up correctly. And that's really good. Sorry, I'm just going to fiddle with some things on my monitor. So, we're setting up the graphic synthesizer. We're sending through a buffer which looks like it's got the correct information in it. We're telling it what kind of primitive we want to draw. We've set up the offset registers, right? There are other registers of note here, I guess. So, you know, back on this diagram, right? The primitive register, the ST register, there's a UV register, there's like which texture, I guess, channel we're taking from. There's a fog register, which, I mean, that's like a whole other thing. Fog is going to be fun if we ever get up to it. But then there's a bigger list somewhere, right, that describes, where are we? GS Users Manual. There's this amazing diagram in the GS Users Manual that shows, oh, not even just diagram, but like this amazing few pages that go through like how centers of pixels are considered, how the rasterizer considers everything, and you know when it decides to draw, like when a triangle is part of a pixel and when it isn't. It's pretty incredible. It's pretty incredible. Texture coordinates. So this is all fine, right? This is all stuff we don't have to worry about yet. I guess the other thing that we were thinking about, right? Where are we? Because we do this conversion to, do we do this conversion? Did I convert a number to fixed bit? Yeah, here. So we convert a number, an integer, to a 16-bit fixed point value, right? So a decimal number with a 12-bit whole part and a 4-bit fraction. And so this is probably something we should wrap up in a function at some point. But for now, I believe just shifting it to the left is going to work, right? Because I should probably leave a comment that maybe explains what this is, right? So if we have AAAA, well, if we have 0xa, right, this is going to go to 0xAO once we shift it 4 bits over to the right. And our fixed point format, right, we're going to have 4 bits. So we're basically saying that it's this 12-bit integer with no fractional part. That sounds correct. That feels correct. So I'm pretty sure what's going wrong at the moment is to do with coordinates and offset. And that's why I had this this wonderful search before, xy offset. Where are we? Yeah, so this function, draw primitive xy offset, which we're calling up here. The other thing to have a look at as well is, I guess, code that uses this, right? So grep xy offset. And I'm pretty sure there's only one function if we get rid of the case insensitive. So if we have a look at the cube example, right? draw samples cube.c. If we look at the cube example, it initializes the graphic synthesizer very similarly to how we do. It stores the frame buffer information kind of differently. But we call this graph initialize function, I think, or are we that graph initialize function? I think we're the graph initialize function, right? I think that's kind of what I've copied here. Screen background color, then initialize drawing environment. we've also done some of this stuff. Oh, hold on. I probably don't want this in the... probably... I copied too much here. I copied one thing too many into... Oh, yeah. Okay. So when we finish drawing, it doesn't actually matter yet, but we definitely don't want this here. But that's fine. So draw... We don't have draw setup environment called anywhere. So what does draw setup environment do? EE draw source draw environment. Where is it defined? Where is it defined? Okay, if I draw source draw.c line 11 draw setup environment. This looks important. This looks very important. This looks very, yeah, this is a bunch of registers we haven't set up. Oh man. Oh, we haven't even, so that means the frame buffer isn't being set up. Okay, this is an important, this is a very important call. This is a very important call. So I guess we just need to do this, right? This is going to DMA it. Does it send? No, it doesn't. Okay, so this is going to shove this stuff into a packet for us. X, Y. But see, one of the interesting things about this function is that it calls, it's going to set these XY offset, this XY offset register to this seemingly magical number, 2048. And 2048 is an interesting number because it's a power of 2, right? 2 to the 11 is 2048. Right, so if we're thinking about our binary representation of numbers, right? Let's just make some space down here. So if we're thinking about our fixed point numbers, y. So 12 bits of the whole number, the integer part, and then 4 bits of the fraction part. If we think about 2 to the 11, right? So this function f to i4 in PS2SDK, this is just converting a floating point number into a 16-bit fixed point number with no fractional part, which is weird, but I don't know why it's called f to i4. Surely it's f to i12 or, I don't know, f to I fp16. I would name this function differently, but what that's doing, it's doing exactly the same thing that my code's doing up above, right? So we're shifting 4 bits to the left. We're shifting 4 bits to the left. This f to i4, it's actually kind of wild. I should show you this definition. F to i4. Helps if you put it in quotes. Draw, include, draw types. F to i4. So, I mean, look at this, right? This is very interesting for code that essentially is just doing, right? So if I was to define this, I would say, I would call it something different for one thing. I don't know. My version of this looks like this, right? Now, the fact that f is a float, I guess, is a little bit different. I don't know exactly how floats behave with this and what the exact details of this conversion are. But anyway, they're essentially doing similar things. I guess there is some interesting stuff going on there. Anyway, I'm guessing it has to be done like that. But because I'm just working with integers, I don't have to use their janky function. So line 70, XY offset. So what strikes me as interesting about this, okay, if we convert this 2048 to a number here, it's going to be 010000000000.0000. And that looks like a surprisingly deliberate value, right? It's almost exactly halfway. It almost bisects the integer part, and I guess by extension, like the whole range of this fixed point 16 format. So I'm not sure if there's something here where it tries to, you know, I guess map the middle of the range. I don't know, it's interesting, right? But the hardware manual does say that the drawing environment has a range of 0 to 4096, which is 2 to the 12, right? Yeah, because, 2048's 2 to the 11, 4096 is 2 to the 12. So I don't know, this seems like it's doing something I don't understand, yet again. So we'll play around with this, we'll see what happens. Maybe I could just, like, set... I don't know. But the important thing here is we definitely need draw setup environment to be in our initialize. That was odd. Bit of Vim magic happening there. So GS init. We need to actually DMA something here. So this is quite messy, but we'll survive. Q equals buff equals draw environment. Again, typos are my biggest environment. This is going to be context 0. The frame info. Oh, and this is why it sets up those bloody structures. Okay, I guess we got to do it. This isn't going to find a definition, is it? Draw buffers. I just need to jump to the definition of this real quick. So, I guess we'll like set it here. FB address that has a width. FB.width equals width. FB.height equals height. FB.mask equals 0, I believe. I don't think I need a mask. Mask. Frame mask. Set frame. Yeah, I'm pretty sure I don't need a mask value, but I actually don't know what this frame register is. So this is like this is the same. This is a different gift tag format, I guess, that we saw before. So this is this AD register again. We saw this guy last night, and what that means is that each I guess entry in this gift tag. So each one of these lines is going to be 128 bits in a gift tag, and essentially one part of our gift tag, I guess. So the first part is going to be data that is getting set to a register in the graphics synthesizer, and the second part is going to be the register identifier, I guess. So in this case, the register is gsregFrame plus this context value. For all intents and purposes, let's just call this gsregFrame 0, because we're not going to be playing with context. We're always going to be in context 0. And the value setting part here, I mean, look, it's doing some bit manipulation, right? It's doing some right shifts, which is interesting. Because, you know, if our width is like 600 and you right shift it 6 times. So what I mean, it's working in multiples of 64, right? Because 2 to the 6 is 64. And you right shift by 6 bits, it's the same as dividing by 64. So the width is working in multiples of 64. The address is working in multiples of 2048. That's kind of cool. So mask, in conclusion, we're going to ignore mask. We're going to set it to 0, but I am just going to double check, because that would be a silly thing to miss. Drawing function, drawing environment, texture mapping. There has to just be like a list of these registers and what they do. Here it is. Frame buffer settings. It's mask. Yeah, cool. So if we set the mask to all zeros, then it basically is like there isn't a mask. That's cool. Draw, include draw. Awesome. So we have our frame buffer. What's the other thing we need for draw setup environment? We also have to set a Z buffer. So this is why I had that Z buffer thing in there before. Is it called Z buffer? Z buffer T Z. Z.address equals, got too many equal signs here. 49 graph VRAM. I'm guessing graph-align page in this instance is 2048, right? Like we're telling this function to get a chunk of memory for this much storage at this many bits per pixel aligned to this value, and that magic number has to be 2048 from what I just saw, because that is what that's what the frame register keeps addresses up to. Beautiful. Okay. Z.width is going to be the same. I'm guessing the information here is just pretty much going to be the same. No. And apparently not. Enable method address ZSM mask. Okay, so z.method, let's just say 0 for now. Z.ZSM equals PSMZ, and Z.mask is 0. Cool. So now we're going to call draw setup environment. Drawing. Setup environment, and this is where it gets big. Context is 0. The frame buffer is the memory address of FB. The Z buffer is the memory address of Z. And now we need to make sure that when we actually draw this, we wait, because again, these things have to stay on the stack while our DMA is happening. Otherwise, bad things will happen. And I wonder if there are actually any restrictions about DMA from the stack in general, but I haven't hit it before, so I'm going to assume there isn't. So now we're just going to DMA send channel normal, DMA channel GIF. We're going to send this buffer. Why does that look weird? It's because there's a space after it. And then DMA wait fast. Cool. I wonder if this will work now. I wonder if we can just magically have this work. Alright, there is, of course, I just mixed up DMA send. I just mixed up the this again, the spelling. It's always the freaking spelling. DMA send channel undefined reference. Of course. DMA. Am I actually? I think I'm right. I think it's actually channel send normal, right? I think. No? Why doesn't it like the spelling then? Because it doesn't like it either time. I'm linking against the DMA library. Weird. Weird. Oh, we've got some people trickling in, by the way. Hello. Feel free to say hi if you're coming by. You wanna ask questions about PlayStation 2 stuff. You want to ask why I'm bothering with this. Come say hi. Come say hi. No, seriously, it's awesome that anyone would want to watch me bash my head against this brick wall. It's really incredible. I'm also gonna. This is just like spinning away back here. I'm just gonna stop that running for a minute. So for some reason, let me just do a channel send normal. Channel send normal. Channel send normal. DMA send channel normal. Channel send normal. Going a little bit crazy here. Okay, perfect. That was weird. Boot ISO. We're making progress. Bit by bit, we're chipping away at this. We still have a black screen, but one day soon, any minute now, we're going to actually have something happen here. Our buffer still looks good, and that's very, very important. We have... Oh, wait, these are backwards. These are backwards. Are they? This is... Wait, this is... What order am I printing these out in? Wait, these buffers are wrong. So it's really confusing, okay? Drawing this stuff... Like actually printing this stuff out is confusing, and trying to do two things on one line is actually really messing me up here. So I'm going to go in. The problem is that it's left to right. Okay, so I talked about this a bit yesterday, right? This is the 64-bit word number 0. This is the 64-bit word number 1. This is the lowest bit of 64-bit word 0. So, you know, if you look at this as one quad word, right? This is the 0th bit. And this is the 64th bit, right? So that's kind of weird. It goes this way, and then it goes this way. So actually, we've done this wrong. We were right the first time, and then I fixed it. I fixed it last night, and actually broke it. I think I've got to compare this to the hardware manuals. EE uses manual. I've got a friend in Discord egging me on to share the manual, by the way. Of all the things to get banned from Twitch for, you know, sharing a 20-year-old hardware manual, it's not high on my priority list. Okay. So, it means we were actually right before, and that the double word 0 is actually the first double word. So, I think that means we were wrong here, right? The lowest bit of this double word has to be 0. No, so that was right. I was right about that. Make Docker build. Okay, this looks right now. The registers go in the upper 64 bits. The general flags and stuff go in the lower 64 bits. And then... this should be the... No, but then this one's wrong. Oh, I'm confused, man. So... Where are we? Where are we? Double word 0. Double word 0. Double word 0. Oh, yeah. No. GS prim triangle. And then there should be 0. Except I've said triangle again. And then red, green, blue, XYZ. Okay, come on. Come on. I believe. We're getting closer, okay? These values are looking mighty correct. It's just gonna get closer and closer until it just happens. Red. So where does... Hold on, I want to check my XYZ format as well. Where are we? UV, XYZ, 2, X, Y, Z. So it looks like I've got an X value here, and then the other two X's are 0. Is that correct? Is that what I expect? What are my triangle coordinates? See, that's not correct. So what I should be seeing here is anything but this. The bottom 16 bits, so that's the bottom 4 characters. Have I set? So this first one is correct, okay? We have 10.0 in X, we have 0 in Y, we have 0 in Z. This next one is very much not correct. We expect 600 in X. So what's 600 in hex? Oh, I don't know how to quickly check. I don't know how to say Fox. Where are we? What am I doing? 600 in. The other thing I should probably actually do is just define these numbers in hex. 258. That looks an awful lot. Yeah. So for some reason, here, our x coordinate is in the first 64-bit word. Here, it's in the second. And then here, I'm guessing this is also whatever we've got next. 20. No. No, C8 is not 20. That's much more than 20. That's, what's that? That's 16 times 10, 11, 16 times 12. That's more than 20. It's probably about 400. 0x. C8. Yeah, that is exactly 200. Okay, that's good to know at least. Something's gone very 0, 1, 2, 3, 4, 5, 6, 7, 8. We're not building, we're iterating wrong. And that would be it. So, sorry, I should actually explain what's happening here. I'm a I don't know what rude word best describes it, but I was just adding to this offset, and that's absolutely not what you do in that case. That meant that rather than looking at this as one vertex, this is one vertex, and this is one vertex, I was looking at this, then this plus this, and then this plus these two. I was just offsetting it rather than like actually stepping 3 at a time. So let's see if this actually works now. Boot ISO. That's different again. So that's the right value for 400, right? 400 in hex. No, wait. Did I say 400? I said 600, right? 600 in hex. 0x258. Yep, so this is correct and this is correct. But this is not. Oh no, it is. Yeah. This is correct. This is correct because it's 20. 1 4. That's 20. That's 16 plus 4. 20. But we don't have a y or a z. Something's happened to my y and z coordinates. Okay. Hold on. Hold on. I'm worried about the order of operations here. I don't think I need to be worried about the order of operations here, but I am. Cool. These shifts, yeah, these shifts are fine. I don't need to worry about this. Maybe I need to worry about this. Maybe one of those warnings is actually one of the problems. Cool. So we have an X. We don't have a Y. We still don't have a Z. Very interesting. Very, very interesting. I was so confident those buffers were looking good. Unfortunately not. Unfortunately not. So this is going to be 0, 3, 6, 3, 4, 5, 6. Yeah, so this is the base, and then we add 1, we add 0. time to do the dumbest thing possible and add in a printf line. Wait, hold on. Whoa, what? This is an int, and I'm shifting it over 32 bits. So this is going to obliterate whatever's in this int, right? Because it's a 32-bit type, and the warning was right. The warning was right all along. This needs to be a 64-bit type, and this is probably a good time to define a nice helper macro for this. I64. So we're going to make a macro for left shifting a number as a 64-bit type, because we're going to be doing a lot of bid fiddling like this. So x. So this is just going to be cast x. Let's call it I64, and let's just say int64, and we'll need an unsigned version of this as well, I guess, or a version that just like casts, like reinterpret casts, I guess. We could make a better version of this function. For now, we're just going to say x. We need an extra layer of brackets. Left shift by b, and we're going to use this function here. So shift as I64, this 32. And this is going to not complain. It's going to kill one of my warnings. Yeah, exactly. Got rid of one of my warnings. Perfect. The other one here is probably also valid, but whatever. The colors are not as critical as the position data. At worst, one of our color channels doesn't come through. Oh, this looks like we now have a y coordinate. Still don't have a z coordinate, curiously. The z coordinate shouldn't be problematic, right? The y coordinate, I understand, because you know, we're kind of like shifting it and oring it. The z coordinate shouldn't be giving us drama. We're just this is troublesome. This is troublesome. So now we do the dumbest possible thing, which is we printf, because you can't really debug a PlayStation 2 program. There are options, but we're going to see a lot of printf debugging. Drawing vertex d. It's going to be try base plus 0, try base plus 1, try base plus 2. We need a new line here, and let's also print these out as hex digits, because that's going to be a bit easier to reason about. Perfect. Okay. I00. Why are these always 0? What have I done? What have I done? Try. Oh, I've always set z to 0. Yeah, no, that actually makes sense. That actually makes sense. I was setting z to 0. Let's set z to something non-zero just to see if it works. Let's set it. Let's actually not do a negative number. Let's set it to 1 here. Let's see if that works. It's always good. Pro tip. Set a number to a value if you want it to not appear to be 0. Okay, so that's what we want to see. So we're properly formatting vertices. This buffer is looking better and better by the minute. X, Y, Z. These little 4-bit groups, 16-bit fixed point numbers. Now we need to work out the offset. And this is where we're going to go back and have a look at how this is done in one of the PS2 SDK samples. So we're going to look at draw samples cube. We're going to look at cube.c. So this sets up. We're doing this where we are graph initialize. We've rewritten this function. Initialize drawing environment. We've just called this. Now, draw primitive XY offset, this is interesting. And this is kind of what I was getting at before, right? Like, they're kind of taking this number, which is almost in the midpoint of the range of the fixed point values, and then they're setting this draw finish as well. And then they send it. Beautiful. So when they render, there's a bit of matrix, local view, world projection stuff going on. Local world, local screen are interesting. View screen, like these matrices probably actually have really interesting information about how this stuff gets transformed. Like if we want to understand this offset, we should actually understand what their screen matrix transformation looks like, right? So I don't know what this chain's going to do. I don't know if they're going to go into like a world space that's kind of normalized around 0, 0 and then multiply that into a screen space that's like from 0 to 640 and 0 to 480. Let's see. Okay. Create view screen. So this is making a matrix -3. So is this normalized around -3? Maybe. Like -3 to 3. Create local world, object position and rotation. This is just our object matrix. This is our camera matrix, local screen. And this is just a product of these things. Okay, here we go. Draw, convert, X, Y, Z. This is where the magic is going to happen. Draw, convert, X. Is that defined here? It isn't. Draw, convert, X, Y, Z. Draw 3D.c, draw, convert, X, Y, Z. Okay. So we're taking in this function is super weird. We've got a center and we have a list of vertices. So for every vertex, vertex plus 1 times the center. Plus 1 times the center. So what does this do? What does this do? Output vertices I plus 1 multiplied by the center. So if we're in the range, I guess we're in the range 0. Wait, I guess we're in the range -1 to +1, right? Because then if you add 1 to that, you're in the range of 0 to 2, and then you multiply that by the center. So 0. So let me draw this, right? So if this is our screen, or if this is our, I guess, rendering space, and this is the center is, I guess, let's call it like C. Let's call it C, right? So I guess you could say this is 0 times C. You could say this is 1 times C, and this is 2 times C, right? If this is like C units from the edge horizontally. And then you could do the same thing vertically. So I guess that's what's happening here, right? And the frustrating thing about this is it tells me that if we just set the offset to 0 and manually pick some numbers that are in the range of our frame buffer, it shouldn't matter. So basically this offset stuff shouldn't matter. I could rig something up that emulates this, but I don't think I should have to. I really don't think I should have to. All I'm going to end up doing, if I tell it to have an offset of 2048 by 2048, or 2048 minus the midpoint of my screen, all I'm going to end up doing is adding 2048 to each of my points before I draw them. And I could try doing that and see if it helps, but I don't think it's going to help. Mad Supervillain, thank you. Thank you very much. Huge coding. We're going galaxy brain here. It will be proper galaxy brain as soon as I can actually draw something to the frickin' screen. Okay. This could also be an initialization thing. Is 664 divisible by 64? This is another quick thing to check. 664 divided by 64. No. Weird. 640 divided by 64 does divide. 480 divided by 64 doesn't divide, but or I guess you multiply them together, right? 664 times 480 divided by 64. Okay, this does... The product of these numbers is divisible by 64, so this should be a fine thing to set to set our frame buffer size to. Let's also change this just quickly to a 24-bit Z buffer, because that sounds like it's a bit more standard from what I've seen. Freaking. Okay. We're making progress, though. We're making progress. Oh. Source. Let's see if we can have a look at this graph initialize function. Just make sure we're doing everything. Because, like, are we calling graph enable output? Are we really doing that? GS init. We are calling graph enable output. So we're doing everything in this setup mode. Graph mode interlaced mode. Let's just like copy a bit more stuff from other settings. Graph mode. Okay, so we're just going to change some stuff. We were in progressive mode. Let's try interlaced and see if it helps. Doesn't help. See, the other thing that would be interesting would be if the debugger had like a good way of viewing what was going through what was going through the graphic synthesizer. I don't think there are good options for that. Debug. So yeah, the debugger doesn't really have a oh my god. This is not GTK is not loving me right now. Yeah, cool. I think I just opened a window that's gonna yeah, this isn't gonna really do much for me. It's kind of cool though, so we can actually see our main function here. And we're just in this like infinite loop of nothing, right? Where we have a branch to ourselves. Also, if you haven't seen MIPS before, this is a MIPS 3 processor with some of MIPS 4 bolted on. And so every time you have a jump, there's an instruction after the jump, which also gets executed. So you can actually put an instruction after a jump and then do it while the jump is happening, which is kind of like a cool feature. So literally here, right? I can't remember what LI is. Load immediate, load 0x2 into the AO register, but it does that while it's jumping to this function, which is kind of cool. DMA channel initialize, DMA channel fast, wait, GSINit. So I could step through here and just make sure that everything's getting fired off, but it should be. I don't think I really need to do that. Can I hide the debugger? Yes. Okay. Set frame buffer filtered. So I really just want to go into full copying mode right now. I want to copy something that works as much as I can. The other thing I'm a little bit iffy on, I guess, is graph set screen. Because it looks like that is actually always zero. And like I've already got that set to 0, but we're just going to hard code that in. And then these functions are all just stuff. If we look back at our cube sample, we could graph initialize. Draw graph source graph.c initialize width height. Where are we? Address width height PSM XY00. Yes. Set frame buffer filtered. We set those to 0. So this looks fine. This is good. And a drawing environment, we're also doing this. Draw setup environment. And then they're overriding the primitive, and then they're sending a finish. We're setting up the environment. We should move this awkward extra bit here, just down into here. It shouldn't make a difference. I mean, it might somehow. It shouldn't, but it might. Render. What's render going to be doing? Render, it just builds a bunch of buffers, right? So, and this is actually using DMA in chain mode rather than normal mode. So this is going to be a little bit different just in general. I love that the first thing it does, it grabs a pointer here. It's like, this is our DMA tag, but we can't actually populate the fields of the DMA tag without knowing what the contents are. So then we're just going to move on, and we're going to come back to this pointer later and we grab it up here, and then we like start our list and immediately increment and move on to the next bit of the list. Draw disable test. Draw clear is a super interesting function we should have a look at. Maybe I'll draw disable tests as well as part of my draw. Draw. I guess we have to do that first, right? So GS prim triangle. Q equals draw disable tests. Z, is Z a Z buffer? It is. Z. Z. Yeah. Weird. So again, weird that this takes in a Z buffer as an argument of all things. Draw source draw.c disable tests. All this is doing is I don't want to duplicate this. This is too much bit fiddling. Okay, fine. I'm gonna do something dumb. Again, we're in damage control mode because we're just trying to get this to work. So I'm gonna disable the Z buffer and see if that helps. Actually, maybe I can just do this before I do anything too dumb, defining things in like global scopes. Let's just define this once way up here when we initialize things. Z, but the memory address of Z. Pass it as a reference. Then draw prim start. Okay, so maybe there's something in draw prim start as well, actually. Draw 3D, I guess. Draw prim. Yeah. Okay, so gift tag, we've got a list of registers that we're setting. The first register is the GS prim register. We're setting, see, there is actually more to this register than we're setting. We're setting it in kind of like the minimal way. Maybe we need to set it in the full way. It also sets a color, and that's it. Okay, so maybe, just maybe, we actually need to properly set this up. And I guess we could actually just do this wherever, well, first off, we can do this wherever the hell we want it, but maybe when we set this stuff up, draw prim, let's do it in here. Let's go Q equals draw prim. Oh, but this takes in weird arguments, doesn't it? It does. It takes in this like color, takes in this prim structure. Q equals, let's manually build another gift tag, okay? And let's set in a draw function. We might as well. QT buff. Let's just give ourselves a bit more space. Set prim. Okay, so the first double word is gonna be we've got to say we're setting one register and we're setting it once. We have one loop. This has two loops, but that's because it's setting the RGBAQ register as well. We're just setting this prim register. So equals. We're going to build an abstraction for this at some point, and then we're setting the AD register, which means that we're just setting register E. And then we have to actually, then we go Q++, DW0 equals. Okay. So the first bit is gs set prim. This takes a prim type, gs prim triangle. This takes shading, which I think we just set to 0. Again, I'm going to have to refer to the hardware manual for this just to make sure. The GS users manual, prim, p prim. Yeah, so these are all just like a bunch of bit masks, bit flags, sorry, 1-bit flags. Shading method, 0 for flat shading, 0 for no texture mapping, 0 for no fogging, 0 for no alpha blending, 0 for no anti-aliasing. What else have we got? 0 for this, 0 for how many arguments here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Really, we can just set all of these to 0, which is kind of neat, just kind of handy. And then, so that's the data that gets set, and then we have to tell it which register as well, and that register is gs reg prim q++. And so you can just mash a bunch of gift tags together, like that's fine. So gift tag 1 ends here. You know, this header tells it how long the data is going to be, so that we're just going to have like 2 64-bit words of data. It's going to get written into we're going to write something onto a register directly, and then we have the start of a new packet, and this packet, because of this bit set here, is going to be marked as the end of the transmission. So let's see if that works. And of course, something has gone wrong. Triangle. Have I misspelled this again somehow? This is gs prim. Triangle. How many different ways can I spell triangle in this stream? Triangle. We're gonna get rid of this. We're gonna simplify our format again, right? We did this earlier. We're gonna undo it. We're gonna set this back to 6. Okay, it kind of feels like once you're getting in the swing of this stuff, it's like, you know, seeing the Matrix, right? You're looking at like bits here, you know, 4-bit constants there, and you're seeing a redhead, you're seeing a blonde. This buffer, this looks, wait, hold on. That's not, is that correct? Setting it to 3. Oh yeah, and prim is registered 0. So let me just go back to where we describe, maybe I should just show this manual. It's not very exciting. You know, if I somehow got banned for showing this, it would be the most depressing thing. Data, address. Yeah, this is correct. This is absolutely correct. So we're now setting prim properly. And we were setting it properly before. If these are all just zeros, like we were setting it properly before. But now we're doing it more properly. So the next step from here, it has to be going somehow into the debugger, right? It has to be stepping into what PCSX2 is actually doing behind the scenes. That's going to involve probably like building PCX2, maybe building it from source and then running GDB against it or something, and actually stepping through when these registers are getting set. Maybe. Man, either way, I'm going to walk away for a minute. I'm going to take a break, and I'm going to see if any inspiration comes to me. So stay tuned. I'll be back in a minute. Enjoy my BRB screen. Let me know what you think of it. I think I've done pretty well with it. All right, I'm back. I've been thinking long and hard. I've been staring into the abyss. Man, it's hard, okay? But I think the best way I can proceed is to look at this cube example and literally copy as much of it as I can. Copy it. Well, actually, I think there's a sampling graph as well, right? Samples. That's not what I wanted. Graph.c. See, what's this? This is testing some stuff. Like, this is setting things up more similarly to how I want to do them, I guess, without using draw. Oh no, it is using draw. Draw clear. So the other thing we're not doing is calling this draw clear function. So maybe this is it. Mid snaps, too big brain for you. Look, like seriously, this stuff isn't that hard. There's just a lot of stuff to know, right? And like I've been doing this for a little while, you know. People ask about programming. Like they ask me about programming stuff. They're like, oh, you know, why are you good at programming stuff? How did you get good at programming stuff? And the answer is always invariably, I have done this every single day since 2015. And I've been programming since 2006, right? I was like 9 or 10 years old and I started writing code in Game Maker and stuff. I can shoulder a lot of the complexity of this and just blast through it and hopefully start to get some things actually appearing on a screen soon. The other thing I could try, right? I'm not actually waiting and stuff, and maybe the infinite loop here is part of the problem. So maybe I actually need to draw more than once. As it stands, I'm just drawing once and hoping that's going to stay in the frame buffer. Maybe that is naive. So we're gonna have a drawing loop. Clear. We need to actually clear the screen. Draw. We need to actually draw. Wait for VSync. We're gonna actually lock into 60 FPS because, you know, the PlayStation 2 is ultimately an analog system. I think we might need to wait. Okay, DMA wait fast. That's fine. This is interesting as well, actually. It puts everything in one buffer, and so then it only has to call wait at the start of the next frame. So it draws, then it waits for VSync, and then it waits for the DMA. So hopefully, you would usually hope that by the time you get back around in this loop, your DMA is absolutely finished. But this is a cool little detail that I like. First thing we're going to do, we're going to call draw clear. We're going to build this buffer. We're going to do this really dumb pattern again. 50. Let's make it 100. Okay, so we're building a list. Q equals draw clear Q 0 0 0 width height 664 480 0 0 0. I don't know what all these zeros mean. We're just gonna roll with it for now. Q equals draw finish. Interesting. So this calls draw clear and then draw finish, I guess, to like commit that draw to the frame buffer, right? Then it's gonna send that and wait for VSync. And then it's gonna draw again and wait for VSync. So this is drawing twice in a frame. This is drawing it at 30 frames a second rather than 60 frames a second, right? Because we're waiting for VSync twice in this loop. Oh no, we're not. No, we're not. We're waiting for VSync once at the start. Let's do this the same. Let's do. Okay. Sorry. I'm getting too excited here. Let's in GSINit. Like we're doing a DMA transfer now anyway. So let's Q equals draw clear 0 0 0 width height 0 0 0 and Q equals, yeah, and then we're sending a finish. maybe this needs to be part of the same. Okay, we can. Oh, we did this to do. Be in the same GS packet. So maybe rather than having our own special transfer afterwards that sets the finish register, maybe it actually needs for some reason to be part of the same packet. And that might be something that's contained in the hardware manuals as some like weird hidden detail. So now when we initialize the screen, we're actually clearing it. And now every frame, gift set tag, this is fine. So set the 80 register. This is setting things the dumb way, I guess, the slow way. And then Q equals packet data. But does it clear the screen? I guess it doesn't. It just draws the same thing over and over. But actually waiting for VSync, I suspect that will actually do something to make it draw. So draw, let's do it. Draw, wait, finish, graph, wait, VSync. And what happens if we build this now? Draw clear, declared here. Too few arguments. Somehow this isn't enough arguments. Context, X, Y, width, height, RGB. Oh, I didn't pass it in a. I need to pass it in the actual list, the actual buffer we're building as well. And then, well, that's not clear either. If they're not clearing, we're not going to clear, because we need to actually like do another DMA transfer then. Boot ISO. We're spinning. The wheel's spinning, but we're still not there. We're still not quite there. I feel like we're getting closer. We're getting critically close to actually drawing a triangle to the screen on a PlayStation 2 or on a PlayStation 2 emulator. And once this works, I'll film it and then like record it and put it up somewhere. Okay, let's think smaller. Let's think much smaller. Q equals draw clear. Okay. What are we saying? Q00. What is it? Context X, Y, width, height, red, green, blue. Let's say 50, 50, 20. Let's actually just try drawing a color. DMA channel send. I've forgotten the order these words have to go in again. DMA send. DMA channel send normal. Send normal. DMA channel. We're sending it to the GIF, the GIF, or the GIF, I suppose, if you will. Q minus buff 0, 0. DMA wait fast. Q equals draw finish. Let's just try clearing the screen to a color and see if this works. TLB, oof, ouch, that is rough. So TLB miss, the translation look-aside buffer, it's a thing to do with memory mapping, I guess, right? It's a memory thing. Somehow we're not doing the right thing with memory. So here's a thought. Keyword T buff. Let's put this outside of the function and just see what happens. Similarly, like none of these actually conflict with each other. Everything is going to be waiting after it's done. So for now, we're going to play with fire and use a statically declared, this has to be declared like before anything uses it because C's fun. We're going to use a statically declared buffer and just hope that it like ends up in a nicer spot in memory, and maybe that's enough to make it magically work. 33 Q undeclared. Q equals buff. Where else is it undeclared? 89. Oh yeah, I deleted too much, didn't I? Q equals buff. Q. I got overzealous. Keyword T. And there's another one on 104. No, there isn't. That should be fine. Left shift counts. Line 62 also has. I got overzealous. Main.c 62 keyword T Q equals. Again, this is jank. We're getting desperate now. I just want to see something happen. Okay, I don't want to see TLB anything, and I don't, and that's good. So GTK center of assertion. GTKs. I don't know what this is. This is just like UI, weird like window environment stuff. It's probably because I'm using DWM, and PCSX2 does not play nice with DWM, as I'm very quickly learning. Okay, so even if we just set the screen color to clear to something, that's not showing up. So that is bad. This initializes the DMA channels, initializes, in a drawing environment, render, free, blah, 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 blah. Okay, so init GS. And we're calling this function, right? We're calling graph initialize. No, we're not, but we're emulating graph initialize. And actually this should look like what we're doing here. Graph set mode, field or frame, and then enable or disable. Interesting. I don't know why this is graph disable. Surely it should be graph enable, right? Maybe it should be graph disable. Maybe that's what's going wrong here all along. Maybe I misunderstood what that flag meant. Let's just try changing a random flag. If that worked, I would have been really upset. Okay. Worth a shot. I should actually check what all these arguments mean at some point. Graph disable, graph set screen. This is fine. Background color, yep. Frame buffer filtered, yep. Enable output. That's the very important one, and it works. So that's good. And then init drawing environment, we're also doing here. Draw setup environment. Draw finish. Are we doing a draw finish? See, we don't have a draw finish in this. Okay. I'm going to do the thing that I said before. We are going to add, where is it? Rather than this just operating in a vacuum, actually, we're gonna, everywhere we have a GS finish, we're instead just gonna call draw finish on the same buffer, right? We're gonna call it kind of inline on the same buffer. Q equals draw finish Q. And what this is going to do, hopefully, is mean something very special to the graphics interface. So anywhere there's a GS finish. Q equals draw finish Q. And I want to manually do this fiddling eventually, but for now, we're going to fall back on these functions. Because these are important things to know, right? And somehow this still doesn't work. See, at this point, I don't know what we're actually doing differently, right? Our initialize function is correct. It just is correct, right? Draw setup environment. Okay, let's undo this. Let's undo our initialize, some of our initialization. At the start of our render loop, it wants us to clear the screen, so we could do that. Draw wait finish, draw wait vsync. Like, I literally want to copy this as closely as I can. It's definitely running the right thing. I guess we could check the debugger. Man, this wasn't meant to take this long to just get something drawing to the screen. Was not meant to take this long. Where are we? Let's break. Draw, wait, finish. That's a good thing to be waiting for. Where are we? There's somewhere you can check like function names, right? Draw clear. Draw. We're right in the midst of. Here. Okay. Like we're definitely hitting the right places, right? GMA channel send normal. Draw wait finish. Graph wait vsync. Let's put a breakpoint here and see what happens. Ooh. Hold on. Maybe actually we're never getting anywhere. So, what if I restart with this breakpoint? With this, hello? No, never gonna hit this. That's cool. Oh no, yeah, no, it did hit it. Okay, step over. Blah blah blah. Channel initialize. Okay. So that's fine. Channel fast waits. And then this draw, wait, finish. This never comes. So we're actually not drawing. Where are we? What happened? Are we stuck in draw, wait, finish forever? We are. Oh, that makes so much sense. The drawer is never finishing. Okay. This we can do something about. This is actionable right now. The power of a debugger. I'm sorry, this debugger is very small. It must be hard to see. But where was this called from? Hold on. Stack frames. Draw wait. Start. Where? So does that mean we're jumping back to here once this finishes? So our draw wait finish in main never goes anywhere. Oh, of course it doesn't. Of course it doesn't, because we're not freaking drawing anything. That's very silly. Draw clear. Q is undefined. Yes, it is. We also were like horribly mistreating that variable q in our main function. It's gonna work this time. We've got to be getting so close. Oh. Steve, thank you. There's a PlayStation 3 now? Man. No, I grew up with the PlayStation 2. It was my first console at home, and I've always wanted to get something running on it, and unfortunately it's a huge pain in the ass. Oh, we're getting close. I can taste it. So let's go back to our friend the debugger. Okay. Run. Oh shit, we have a breakpoint set. That probably isn't good. Let's just like not have breakpoints set. Isn't that a good bonus? Did that actually run before? Imagine if that actually was like it and I missed it because the breakpoints were set. So our function table is gone, but that's okay because we're at main anyway. Let's break here and reboot. And let's just step over some stuff and see if this halts, when it halts, see what's going on. We're actually hitting our infinite loop here. And then we get stuck on vsync. See, there's something really strange going on. Yeah, getting this stuff set up is frustrating. I was saying last night, there's something actually really refreshing about developing for what is essentially an embedded system, right? So on the PlayStation 2, I gave a quick demo of this last night, right? But I can just go like volatile int foo equals I can just pick an address in memory and I own this address. I can set anything I want to it. Any valid memory address as far as the memory map is concerned, I can just write to. There's no operating system to get in your way. You have full control of the whole hardware of the system. So that's kind of cool. Once you get over the initial hurdle of working out which things need to be set to actually get a triangle on the screen, you have a lot of power. And like, you know, my draw function up here, I'm literally just manually, for now, I'm going to build an abstraction to do this eventually, but just like manually setting these raw bit values that tell the graphics controller, I guess, how to set registers in the rasterizer, which will then influence how triangles get drawn. Like, it's crazy how much power you have and how much you can do just by twiddling with bits. I find the OpenGL stuff, it's more working out, you know, you're interacting with like Windows libraries, you're interacting with like X11 libraries. You've got to understand how that stuff works. You've got to understand how to get a buffer. If you're doing like driver level stuff, then you get a bit more into this like weird bit command hacking stuff when you're sending stuff to the GPU. But like, I don't know, it's kind of exciting developing for a system that has like no rails. This vsync never seems to be getting hit, which is weird, right? Like, we're never advancing beyond vsync. So why could that be? We've set something wrong up with graph. One of our graph functions has to be wrong. Our mode maybe is wrong. Maybe we're using a mode that doesn't exist or that is invalid somehow, and that means that vsync isn't behaving properly. We are, however, waiting for vsync here, and that's fine. So that's weird. That's really weird. Unless the debugger's just being weird. I don't know. Okay. Oh, it's because we had a freaking breakpoint there. Is that it? Where are we? Stack frame, draw, wait, finish. I don't know what happened. Okay, hold on. Let's go back. Let's go back to our friend. Let's jump out here. And let's make sure we don't have any other stray breakpoints that are going to mess us up. And let's reboot. Segmentation fault PTSD. No seg faults on a PlayStation 2. Seg faults are an operating system concept. On a PlayStation 2, you're... Oh, well, well, I don't know. Are seg faults an operating system concept? As far as like a Linux seg fault goes, or like a Windows seg fault goes, you know, that's like you're writing to an address that the operating system says no about. On the PlayStation 2, if you write to an address that's invalid, the system just crashes, right? It just dies. You get an error screen, maybe it generates like a hardware exception, something interrupt, maybe, I don't know. But it's very different to they're a hardware thing. The PlayStation 2 does have a memory mapper, so it does have some concept of like valid address, not valid address, but it's different. It's the same concept, but in a different way. There's no recovery from it on a PlayStation 2. It just tanks the system, which is really fun. What am I? Oh yeah, I'm stepping through this in a debugger. Okay. So, we've broken here. We're going to step over. Step over. And for some reason, this is like flagging me up here. I don't know what that means. What does that stack frame look like? Draw finish. It says we're in draw finish. So does that mean that it gets stuck at draw finish? What if I just don't wait for the draw to finish? But like, I feel like this is the wrong approach, because if draw finish isn't getting called properly, that means we're not drawing properly. So there is something wrong with our GIF tag. Just handle the kill signal. Yeah. Step 1, write an operating system that has a kill signal. There is actually a Linux port. I think it's called Black Rhino, and I think they've got a Linux 5 kernel now running on a PlayStation 2, which is really cool. I haven't played with it because I only have a slim PlayStation 2, so I can't have a hard drive attached to it, or I can, but it's not really very good. I want to get a fat PS2, get the hard drive adapter, get an IDA hard drive, plug it in there. That would be awesome. Shout outs to everyone coming and watching, by the way. I can see my viewer numbers trickling up a little. It's very exciting. It's awesome that, you know, usually I would sit here on a weekend and do this It's cool that people want to come and watch rather than me just like staring into the void alone. Okay, so is there something at the start of the gift tag that's wrong, right? Could that be it? Because all draw finishes, vi ee draw source draw finish. All it is an extra gift tag. What compiler am I using? This is a open source toolchain. Let me hold on. Do I have it up somewhere? It's GCC. All of the PlayStation 2 development has been done on GCC historically. Let me actually pull up the proper GitHub link. So there's a toolchain that has like a bunch of stuff with it, and then there's also in the PS2 dev project, they've got like a port of a bunch of stuff. They've got GDB. There's a port of newlib as well. PS2 toolchain. So this like builds GCC and bin utils and stuff for the Emotion Engine, which is like the combination of a MIPS, what is it, a MIPS 64 R5900 CPU, which is a MIPS 3 CPU with 2 vector units, which are completely unique hardware. So it builds an assembler for that as well. It also builds an assembler for the IOP, which is a MIPS 3000 something. It's the CPU that was in the PlayStation 2. So another MIPS 3 CPU. So yeah, GCC, MIPS 3, plus some customizations. Okay, so draw finish. This looks good. This looks fine. Do we... And then this waits for the draw to finish. It doesn't wait for the DMA transfer to finish. Q minus, buffer, packet data, DMA, channel, GIF. This looks like we're doing everything they're doing. We're not waiting before we do it. I guess that's the other thing we could try. DMA, wait, fast. I guess that's the other thing that we can try, right? God, I keep going to the wrong scene here. Or the wrong screen, rather. Okay, come on. Still nothing. Still no pulse. Nobody home. Let's just make sure there's not some, like, weird value thing going on. Nah, weird. Weird. It's also, I guess, double check. Like, maybe we could just copy this function directly, one for one. See if it does anything different. I guess the other thing is we should probably... Like, maybe we should wait for a draw to finish. Okay, we need draw, wait, finish. And we need it to actually finish drawing. Maybe... I mean, we shouldn't need to... Oh, we should need to clear the buffer. We should absolutely clear the buffer. We don't need a new function for this. What order the arguments? I can never remember the order for the arguments of memset. Hold on, it's pointer length, pointer value length. I think memset. Oh yeah, I need stdlib. Incompatible implicit declaration. Oh yeah, it's from strings, sorry. It always feels like that should be a stdlib. Wait. String. I've been doing too much Golang, I'm trying to include strings. Let's see if this was it. Because if I'm not zeroing my gift tag, then it's just going out and reading some extra garbage, which isn't good, which is not good. I should probably just memset this a few other times. And again, pointer value number. Yes, that is that's the order I'm going with. Beautiful, perfect. It's always nice when you remember something the right way. So, and this is the first thing to use it, so I don't need to worry about setting it. So, init, that's fine. So I'm only using it. I'm using it here. Should I just like... I mean, it can never hurt to zero out your buffer extra cautiously. I was really hoping to be cleaning some of this stuff up into nicer abstractions by now, but we are still we are still struggling to get a single pixel onto the screen. But we're gonna get there. We're gonna get there. Oh. So maybe graph mode field. I think, like, what mode is this graph example? Graph samples graph.c. What mode is it actually using? EE graph source graph .c initialize. It initializes itself in interlaced mode by default. Graph. So graph mode interlaced, video mode, mode field, mode enable. Mode is from graph get region. Well, let's do that as well, because like we're just gonna copy everything. Int v mode equals graph get region. If this works suddenly, that'll be incredible. I don't like this resolution, by the way, though, right? Why is this 853 by 480? Maybe I just need to set it flat to 640. Actually, yeah, what resolution is this using? Hold on. That's the thing that I haven't copied. I've copied, like, all this, frankly, useless crap. Let's do the draw sample, because I think that's in a more sane mode than 512 by 512. Where are we? Frame buffer width 640 by 512. Yeah. See, like, let's try that exactly. Because frame buffer sizes are really important for actually getting the stuff to draw. Why can't old consoles have a developer-friendly SDK? Honestly, this is pretty good. For a community effort, it's good. And there are nicer... thank you for the follow, by the way. Anakim Luke. No, so there's a really cool library for the PlayStation 2 called GSKit, which I've played with in the past, which does like CPU rendering really well. It's really good for 2D stuff. It does some simple 3D stuff. I could probably... Like, I've hold on, if I go to my website... I can see a nice picture of something I drew with it. Unfortunately, I lost the source code to this, but like I have done some drawing. This is actually like running. This ran like this on a PlayStation 2. This screenshot was taken from an emulator, and I had like a little spaceship game going. CPU rendering, yeah. So doing all of your vertex transformations and stuff on the CPU, and then just piping those into the rasterizer directly. The PlayStation 2. Hold on. So. I kind of drew this picture yesterday, right? You've got the CPU, which is called the Emotion Engine Core, and this is your MIPS CPU. You have two vector units to the side. Vector unit 0, vector unit 1. These are really weird to program. They have like a 128-bit instruction set. Vector unit 0 is a coprocessor. I think it's coprocessor 2. For the EE core, and then you have the GIF, which is what we're trying to talk to at the moment. And behind the GIF is the graphics synthesizer, or basically a fancy rasterizer. So all of your communication to the graphics interface is done either from the EE core or from Vector Unit 1. This is called Path 1 rendering, this is called Path 3 rendering. If you want to get good performance out of a PlayStation 2, you want to send data via main memory from the CPU into Vector Unit 1 via a unit called VIF1, which is kind of like the GIF here. These are individual chips. The heart of the CPU, the heart of the PlayStation 2 is called the Emotion Engine, but the Emotion Engine consists of the EE core, the 2 vector units. I think it might include the DMA controller in that. There's a cool diagram in the system hardware manuals, but they're copyrighted and I'm not allowed to show them to you. But yeah, awesome link. Thank you, Steve. But yeah, different chips. VU0 and VU1 are programmed completely unlike anything else that you will have ever seen before. They basically have 2 MIPS 64-bit instruction sets bolted on top of each other into super 128-bit instructions. They're insane. They're absolutely insane. And I want to get to programming for VU1 at some point. That's the ultimate goal of this. But first, I just need data to come down this path to know that it works. So then I can basically... So step 1 is to render down this path. And this path is always useful because you can send things down these 2 paths mostly simultaneously. So the idea is that eventually you do all of your vertex transformation and all of your fancy work in VU1 and then send that to the GIF. While that's happening, you also send texture data via this path to VRAM, because the graphics synthesizer has a whopping 4 megabytes of video memory. Once you include frame buffers, if you're double buffering, you're lucky to have 2 megabytes left over total for textures and everything else. 128 bits for instructions. So not exactly. It's 2 64-bit ISAs bolted on top of each other, right? So it's complicated. It's complicated. They have really interesting registers. All of their registers are vectorized. So they're 128-bit vectorized registers. So every instruction has options for just writing, for example, like an add. Your destination, you don't just have a destination register, but you have destination fields. So you can just write to the X, Y, and Z, or like just the X and Z, or something like that, right? So they have these really interesting address modes. 4 megabytes. Oh, yeah. So most of that 4 megabytes goes on frame buffers. 2 megabytes is like a solid target for, we're going to have textures and stuff. But also what's interesting about the PlayStation 2 and why this is a really fascinating system. You start off, your vertices go through to VU1 and then they flow through to GIF. Meanwhile, you're sending texture data to GIF, right? But how long does your vertex transform here take, right? So you start this transfer and then there are ways of monitoring data through it, but if you want a really efficient pipeline, you don't check in on VU1, right? You do other stuff in the meantime. The CPU isn't super powerful. So ideally you have a system which somehow kicks data to VU1, then also uploads the texture, and the textures are in VRAM as these vertices come through and go through the GIF and get rendered, right? So that's a really interesting challenge. It's very asynchronous. The games that work well and that use a lot of textures and that really utilize the data bandwidth, I don't know how they work. I don't know how people did it, right? Other than the fact that teams of very smart people worked on them full time for many, many years, right? You can imagine, I've spent 3 hours messing around with this now, and so far I've got nothing drawing to a screen, but I have filled in some gaps in my knowledge of PlayStation 2 stuff, which is good. It's fun kind of playing with this stuff right from the start and manually building these buffers and trying to push this stuff around, like literally just magic numbers everywhere. Start from the very bottom up and then build interesting abstractions that let me do what I want. But in 3 hours, I have not gotten a single pixel put going to the screen, right? Which is crazy. If I had a whole day to sit down and mess around with this, I would get something on the screen, 100%. Trying to talk while I'm doing it as well, right? I get very distracted. I don't know if you can tell. But the point is to have fun doing this, which is good. I wouldn't change anything. Okay, so the thing I was playing around with there was with actually waiting. It was with these draw wait calls, right? Because these were somehow messing up the execution. They were never fully being realized. Printf, that's a very good question. I don't exactly know how printf is implemented. Let's look at it, right? So I've got PS2SDK here. This is a fully open source toolchain. I mean, there are going to be a lot of printfs here, right? This is going to be defined in the IOP, I guess. How do I find the definition? It might actually be a define. It isn't a define. Of course it isn't a define. Okay, so IOP kernel include. So this is something that looks like it's. It looks like it's running. Ah, cool. Yeah. It looks like it's running on the IOP, which is the IO processor, which again is entirely asynchronous, and you communicate with via RPC. So via IOP debug. What line are we going to? 957. That's quite a line number. Okay, well that's just a shallow vprintf, which is just calling vsnprintf. So where does stuff actually happen? This one looks a little bit more interesting. Okay. So in conclusion, it's complicated. Printf is always surprisingly complicated whenever you look at it. The answer is it goes to some magical debugging port, which we're actually able to pull into a log in PCSX2, so we can see it. That was probably a little bit more detailed than you wanted, but for example, stuff gets logged. What's actually interesting as well, I can pull up, I can just like pull up a PlayStation 2 game. I think I've got my stuff mounted. Where are we going? So if I just like pull up an arbitrary PS2 game, let's not show everything here, but like, let's pull up Ratchet and Clank. I meant to reset there. You can actually see a bunch of stuff gets dumped out to the console as it loads. So, you know, some header for some sound library that was written by Sony, right? Some stuff about thread priorities. I'm guessing these are IOP thread priorities, or maybe main. Anyway, you can see that SoundTick has a really high priority and other stuff, blah, blah, blah. It's really cool. And so you can actually check out the logging outputs of real games in PCSX2, which is not very interesting usually, but, you know, it's there. It's something that's there. Okay. We're gonna come back. We're gonna get our friend the debugger out, and we're gonna try this again. Functions doesn't want to give me a function table, which is annoying. I think, yeah, all this draw stuff is not where we want to be in memory. Stack frame. Thankfully, we can usually find main through our stack frame. So, yeah, we're stuck. We're stuck. At frames here, we're never advancing beyond the first draw wait finish. Which is so annoying. Which is so annoying. So our vertex drawing, we're not doing this. Get a buffer, clear the buffer, set the environment, draw finish. Where's our example? Graph, sample, graph. What's it doing? Initialize. It just calls graph initialize, that's fine. And a drawing environment. Okay, draw setup environment. It has a frame buffer, it has a Z buffer. That's exactly what we're doing. Then it has draw finish, which is exactly what we're doing. And then it sends normal. And then it draw waits here. Well, I guess if we draw wait here at least, then we'll know that it gets stalled like right here. But it's really frustrating because you can see we're literally doing the same thing here, right? Unless something has changed in PS2SDK, which isn't impossible, but it doesn't feel like this is the kind of place where a change would matter, right? Oh, this is so weird. This is so weird. Okay, so we'll build that change. Draw weight fast. Draw weight finish. Sorry, I got my I got my functions mixed up. Draw weight fast. So and it gets stuck here at draw weight finish. So that's good at least. We're narrowing down that indeed we are not setting things up correctly. Fast was the one they used in the sample. There are two functions in play here. There's DMA wait fast and there's draw wait finish, which look very similar and are very easy to mix up. So it's possible that I've mixed them up. DMA wait fast, you only need, like, we need to call it before we reuse this buffer, but other than that, like, it should be fine. And we're not even getting to somewhere where it could be an issue if this draw is never finishing. So is there a problem with our Z buffer arguments? Because we kind of half-assed those. Enable address mask ZSM, non-zero ZSM. This is a difference. We're just going to go through these differences until something works. And we're stuck on draw weight finish again. Oh, it drives you crazy, doesn't it? Mask PSM. We're using a sane PSM value. Do I have a project in mind? I just want to push some triangles through, right? Like draw a spinning cube. That's goal number 1. Then I'm probably gonna revive what I had before. I think I had this up here, right? I had this like little infinite scrolling space shooter thing I was working on. I want to make a better version of this that it actually uses a bit more of the full power of the PlayStation 2. It still won't look very good. I'm not much of an artist. You know, it'll still be like programmer art, but these are models I found online, right? This was kind of what I was playing with when I was in lockdown last year. So this stuff was like a year old, and unfortunately the code was on a virtual machine that somehow died. And so like I hacked some stuff out in a week, and then I never pushed it to GitHub or anything, and I lost it. It wouldn't be hard to recreate, but I'm trying to go down. So this was like using a library that had a much higher level of abstraction. I'm trying to go down a level, start nitty gritty, and then build my own abstractions, because I think that's a bit more interesting and a bit more exciting. Maybe I'm a bit crazy, but you know, we'll be fine. Okay, I'm going to call graph initialize instead of doing this myself. I think that is the ultimate conclusion to my, like, if this is the answer, I'll be kind of annoyed. But anyway, graph initialize, spelling's hard, fb.address, width, height, psm 0, 0. I mean, this shouldn't make a difference because we're just literally replicating that function at the moment, but we're going to do this. And we're still stuck on draw weight finish. Oh, it does your absolute head in. I hate it. I absolutely hate it. Oh wait, we changed our... Let's do one more thing here. No. We're still stuck at draw weight finish. Oh, this is insane. This is insanity. What if I go back? I mean, maybe clear doesn't even work like this, right? Like maybe clear is misbehaving here. Maybe I don't know. Going a little bit crazy. Draw weight finish never returns. It doesn't even get to clear, right? That's the frustrating thing. All about the mindset. Oh yeah, I like that. Change the problem. Okay, I'm gonna try another crazy thing. We're gonna call malloc. Maybe the it shouldn't be, but maybe the buffer, maybe the actual address is an issue. Buffer malloc. Let's make it. So these are quad words. Let's make it 100 quad words long. That's what we had before. And that's going to complain because we haven't pulled in malloc from stdlib. Let's just see. Maybe it's picky about where you actually DMA from. That looks promising. That looks very promising. That looks like it actually ran the freaking code. Whoa. Or not. No, hold on. It just gets to a different weight. Yeah, you've got to be worried about statically allocated stuff when you're like sending memory between processes, I guess. Okay, well this gets past the initialize, right? Where is it? DMA channel initialize, graph get region. Draw weight finish, graph weight. Where are we jumping? Graph weight vsync. And this is our infinite loop. Where's GS? Oh, there it is, GS init. So we get past GS init. Crazy. Absolutely crazy. And then I think what we're doing, we're calling draw weight again, which of course does nothing because we've just waited for a draw and we haven't done another draw since. So now if we run it again, it works. Oh, that feels so good. Oh man. 2 hours of staring into the abyss, of stepping through things with a debugger. That is an incredible feeling. Red rectangle. Okay, let's go. Let's do something crazy right now, okay? Let's change a red rectangle. Let's make it a blue rectangle. Well, let's make it a green rectangle, sorry. Ready? Let's get rid of this. Hold on. Let's change a red rectangle into a green rectangle. And it works. Oh, that is so good. That is so good. What's a nice clear color I can use? What's a nice clear color? Let's go like 20 for now. That'll have to do. And now, oof. Rather than we're gonna take in a buffer and return a buffer. We're gonna put this all in line. We're not gonna do anything too crazy for now. Draw finish. This is fine. This is fine. And we're gonna return Q. Okay. Let's see if we draw a triangle. Not quite. I mean, that was ambitious, right? But we're getting there. We're doing it. We're doing it. It's real. Ship it. Okay, so now we're back to just working out why our draw function doesn't do anything. I was talking about offsets and stuff before. I thought that was going to be like the main hurdle for today's stream. I actually think that's a good place to call it. It's been 2 hours of me trying to get a single pixel on the screen. It's finally worked. I'm going to end on a high rather than delving back into confusing, weird stuff again. So thank you so much for tuning in. I've been Tom. Do I have backface culling enabled? Interesting question. Interesting question, actually. But yeah, I'll think about that one, and I'll be back next time. By the time I stream next, which will probably be Wednesday, Australia time, I will have a YouTube channel up for this stuff. So I'm going to upload my streams to YouTube. I might do some other videos and stuff as well on the side. Thank you so much for coming and watching. Like I said, I really didn't expect anyone to tune in here, so it's been awesome having some people hanging around. Steve, Anakin, Luke, Mad Supervillain, you've just been lurking around in the background. So glad you enjoyed it. Man, red rectangle, step one of many. Hopefully next time we can actually get some triangles drawing and start to refactor this code into some nicer abstractions. That's the goal, that's the dream. I'll I'll link my website in the chat on the way out the door. Thank you so much. I've been Tom. I'll catch you next time.